Hello. In our last video, we introduced the concept of Markov Chain, and in particular stationary Markov Chain. We introduced this important Markov property that says P of xn plus 1 equals k. That is the probability of the random variable at step n plus 1, conditioned on previous states of the chain, depends only on the state of the chain at the previous step xn. This says that the probability of future events depends only on the present. That is, if I know the present, that's the only information I need to make the best possible prediction of the future. Additional information about the past does not help me. Now, stationary increments means that these so-called transition probabilities do not change over time. In other words, this conditional probability does not depend on n. It doesn't depend on the particular step I'm looking at. It just says the probability of the next step events, depending on the current step events, is given by a fixed number, which we call a transition matrix element. And that's what we refer to down here as PJK. For Markov chain, the state space is discrete. We typically look at a finite set of states as our state space. Notice this has n plus 1 states. The sample space is the space of chain sequences, which is going to be an infinite sequence where each element of the sequence is a number in the state space. So those are the possible outcomes of the chain. These transition matrix entries are called one-step transition probabilities. They're non-negative. And the sum of the transition probabilities from state J to all other possible states K is equal to 1, because from J it has to go somewhere. Some examples of matrices. Notice the property that the row sums are 1, column sums may not be 1. These are the from states, these are the to states. And we had reached this point of talking about a probability vector. Now suppose I'm at a certain time and I don't know which state I'm in. I only have a probability distribution of where I am now. I have incomplete information. In particular, we deal with probability vectors if we start in a definite state and then run the chain for several steps forward. Then at each time the transition matrix will generate a new probability vector, and probability vectors satisfy the properties that you expect of a set of probabilities. If I only have possible states from 1 to m, then the sum of all probabilities for those states must be 1. Now that's this property here. And of course probabilities must be non-negative. Now there's a slight error here. This should be P0, P1, according to our previous convention. So I'll make that change here. This should be P0, P1, and so on. And this should be the sum from 0 to m, if we're consistent with our previous notation. So let's see some examples. These are all probability vectors. The first one involves 5 states. So your state space would be 0, 1, 2, 3, 4. Second one involves 3 states. Your states would be 0, 1, 2. Third one involves 4 states, 0, 1, 2, 3. Now, of course, this is not a probability vector because they don't sum to 1. And negative numbers also do not give you a probability vector. All right, so let's characterize some properties of transition matrices. A square matrix P is called a stochastic matrix if each of its rows is a probability vector. A more general definition is a square matrix P is called a substochastic matrix if the entries are between 0 and 1 and the sum of each row is less than or equal to 1. Now what's the interpretation of a row of a transition matrix? In fact, the ith row gives the transition probabilities from state I. And that's why the rows sum to 1. So I'll just denote that here. Okay, the ith row of a transition matrix gives the probabilities of moving from state I to all other states. Now we have examples here and so on. So here's a fact about stochastic matrices. A convex linear combination of stochastic matrices is a stochastic matrix. Now what's a convex linear combination? What it means is you take for any number, sometimes it's called alpha, between 0 and 1, then a convex combination of x1 and x2 is alpha x1 plus 1 minus alpha times x2. Now notice in the case when alpha is 1/2, this is just the average. So it's kind of like a weighted average. Now he has a more general definition of convex linear combination. He's taking a combination of an arbitrary number of stochastic matrices. So instead of alpha and 1 minus alpha, he has these numbers ai, which are the weights, and the weights sum to 1, and you take the sum of weights times stochastic matrices, and that will give you still a stochastic matrix. Now I'll let you read this proof. In fact, we don't use this in the subsequent discussion, so I'm not going to spend a lot of time discussing it. Now here's something more important for us. If P1 and P2 are stochastic matrices, then the product is also a stochastic matrix. In particular, if P is stochastic, then P to the n is stochastic for all n greater than or equal to 1. Now you can read the algebraic proof here, but I want to give some intuition of what's going on here. So let's look at an example. Here we have a transition matrix with from states and to states. So moving from 0 to state 0 is probably 1/3, and so on. I can write this in terms of conditional probabilities. The probability that xj equals 0 given xj minus 1 equals 0 is 1/3. Probability xj equals 1 given xj minus 1 equals 0 is 2/3, and so on. There's two more conditional probabilities conditioned on the condition that xj minus 1 equals 1. So in this case, what's the probability that xj equals 0 given xj minus 2 equals 0? Well, what can happen? If I start from 0 at time j minus 2, then I can move to either 0 or 1. And these probabilities are given by P00 and P01. Now if I end up in state 0 at step j, I would have to move from 1 back to 0, or I'd have to move from 0 and stay at 0. So in fact, the probability of moving from 0 back to 0 is a sum. These are two disjoint ways of reaching 0 from 0. So what I actually am doing is summing over the intermediate states that it can reach. I go from 0 to any intermediate state, and then I go from any intermediate state back to 0. This is actually called the Chapman-Kolmogorov equation, and you'll see a section on this in the book. Now if you know something about matrix multiplication, in fact this is the 0, 0 entry of p squared. If you write down the two matrices and perform the product, you'll see that that's true. And in fact it's going to be true in general. If I go from state j to state k, I can go through any intermediate state, and each one of these different paths is disjoint. I sum over the disjoint paths, and in fact what I'm doing is I'm doing a matrix multiplication. And if I start in state j and end in state k, this is going to be p squared jk. All right, so that's the intuition behind this. Now what we've done for 2 steps you can do for any number of steps. So the wonderful property of Markov chains is that if you want to know multiple step probabilities, you just multiply your transition matrix that many times. All right, let's go back and see if we've got everything here. All right, so that's the statement of theorem 1.2. If P1 and P2 are stochastic matrices, then the product is also a stochastic matrix. Now, in my example, I chose the two P's as equal, but the same reasoning holds whether or not the two transition matrices are equal. And I mentioned this, if P is stochastic, then you can do this product n times, and that will give you the n-step forward transition matrix. Now, an important property of probability vectors is if you take a probability vector and multiply by a stochastic matrix, then it's still a probability vector. And that makes sense because you're modeling a practical situation where you have several states and your chain is in one of those states with some probability. And then the transition means you move around in a probabilistic way, and you'll still have a probability distribution. And you can read the algebraic proof here. All right, let me clarify this notation here. This P with a single underline is a probability vector, and this P with a double underline is a probability matrix. So he's taking the probability vector times the probability matrix. And that's still going to be a probability vector. So basically in the proof what happens is the product of the vector times matrix gives you one sum. You're starting in state S and you're moving from state S to state I. That's I there. And that will give me the probability of being in state I. But then if I sum over states I have this double sum, and I end up summing the row of the stochastic matrix, which gives me 1, and that means I have the sum of the entries of the probability vector that I started with, which is this P single underline, and that's equal to 1. We see here we have a product of two sums. This is the sum of the entries of the probability vector, giving me 1. This is the sum of row S of the probability matrix, which is also 1. So I have 1 times 1 equals 1. And that shows that if I take a probability vector and multiply by a stochastic matrix, I get as a result another probability vector. Not the same vector, but it's still a probability vector. Okay, let's stop here.